As we get into chapter 8, we're going to be talking about nuclear change. Now, we've been talking about some other kinds of changes before. We've talked about physical change, and we said that physical change will change the appearance, but not the composition of a substance. So if you cut a substance in half and make it smaller, if you chop it up, make it really little, if you grate it up, if you change the state, if you take water as an ice cube and you melt it so that it becomes a liquid, if you then boil it and it becomes a gas, all of those things are physical changes, but you still have water in every single case. So physical changes don't change the composition of the substance that you have. We also talked about chemical changes, and chemical changes will change the composition of substances. And the way they do that is that we're breaking chemical bonds in one substance, or in two substances usually, 3, maybe even 4, and then we rearrange how those atoms are hooked together by forming new chemical bonds, and we rearrange the atoms into new substances. So chemical changes mean that you're not going to start with the same thing that you're going to end up with later on. And we talked about a number of different chemical reactions. The burning of fuel was one example. If you have propane to heat your house and you react that with oxygen to burn it, then you end up with carbon dioxide and water, which is certainly very different from what you started with. So you've broken bonds, you've rearranged the atoms, and you've made new bonds and then new substances. In this chapter, though, what we're talking about is a nuclear change. And so it's a change to the nucleus of the atom. And when that happens, we actually are going to change the composition of the nucleus in order to change the kind of atom. Now, if you recall, what we said was that the number of protons in the nucleus of the atom tells us what kind of atom we have. It tells us what element we have. And when an atom undergoes a nuclear change, the kind of atom actually is going to change quite often to a different kind of atom. You will recall that we said the nucleus of an atom is made up of protons and neutrons. Now, normally protons should repel each other because they all have a positive charge. But there is a specific kind of force that holds that nucleus together. It's called the strong force. And it's called a strong force because it is the strongest force that mankind is aware of. We are aware of gravitational force, which keeps us anchored to the earth and doesn't allow us to float all over the room. We're aware of an electromagnetic force that is going to be the force between charged particles. And we know that positive particles are going to repel each other. Negative particles are going to repel each other. A positive and a negative charge are going to attract one another. So we talked a lot about electrostatic or electromagnetic charges when we talked about electricity, when we talked about friction and those types of things. So the strong force that holds the nucleus together is stronger than either the gravitational force or the electromagnetic force between charged particles. And so that strong force, even though that there are going to be electromagnetic forces that are going to push the protons apart, the strong force is stronger than that, and it will hold those protons and neutrons together. Now the thing is, this only operates very, very short distances. So you can almost think of it like Velcro. You know, Velcro, if you've got one piece here, like the fuzzy piece on this side and the piece with all the hooks on this side, if you've got the two pieces of Velcro this far apart, they don't do anything. They have to be touching each other in order for those pieces to actually grip and hold each other together. So you can almost think of the strong force kind of like Velcro. You've got to have a very, very short distance between the two particles in order for that strong force to be able to really hold on to anything. You also, we know that we have to have the proper number of the proper ratio between the number of protons and neutrons in the nucleus. And if that ratio gets out of whack, then the nucleus becomes unstable. We also know that the strong force isn't very effective if the atomic number gets over 83. And so remember, the atomic number is what tells us how many protons are in the nucleus. So if you have more than 83 protons rather in the nucleus, the strong force isn't able to hold all of those protons and all of those neutrons together. You can also kind of think of this like a water balloon. The latex of the water balloon is going to hold all of the water in place in the water balloon. If you've ever overfilled a water balloon, you know that the balloon is going to explode. And so similarly, if you have too many protons in the nucleus or too many neutrons in the nucleus, the strong force can't hold it together. And so it's actually going to end up breaking apart because the nucleus is too big at that point. And remember, we said the strong force only acts over very, very short distances. And so what happens when the strong force is not strong enough to hold the nucleus together? Well, then your nucleus becomes what we call radioactive. And radioactive, did I spell that right? Yeah. Radioactive just simply means that the nucleus is not stable and it is going to decay into a smaller nucleus. It's going to break apart, it's going to lose some particles, it's going to lose some energy, it's probably going to lose both in order to get the nucleus down to a size where it is stable and the strong force is able to hold that nucleus together. The vast majority of atoms in our universe are stable, but what we're going to be focusing on in this chapter is those atoms that are not stable. We're going to talk a lot more about that in the coming days.